Hello guys, welcome back to my channel. And in the last video, we were tackling some questions from MIT Integration B qualifying round 2020. We did questions 1 to 10 in part 1, and now in this video I'll be doing the remaining questions 11 to 20. So let's get started. Okay, so question 11, let's define with I. uh, to be integral from 1 over root 2 to 1 of arc sine of x over x cubed dx. Now, for all of those who are uncomfortable with such type of notation, I would like to just rewrite this as integral from 1 over root 2 to 1 of arc sine is nothing but sine inverse of x over x cubed dx. So notice we have an inverse trigonometric function, and even the upper and lower bounds look like their angles. Rather, not angles but values of sine. So this is 1, for example, is sine of pi over 2. 1 over root 2 is, for example, sine of pi over 4. So let's go ahead and do a trigonometric substitution, because that's the only logical thing to do at this point. So let x is equal to sine theta, and dx therefore is nothing but cosine theta d theta. And when x is 1 over root 2, I said theta will be pi over 4, and when x is 1, theta will be pi over 2. And we have sine inverse of sine of theta over sine cubed theta and cosine theta d theta, like this. So sine inverse of sine will just be theta. So if theta, and this is we can write this as cos theta divided by sine theta times 1 over sine squared theta d theta. I just split the sine cubed in terms of sine squared and sine, because we can write this as integral from pi over 4 to pi over 2 of theta times, this is cotangent theta. 1 over sine squared can be written as cosecant squared of theta d theta. And at this point we can use integration by parts, because these two functions can be integrated easily, because the derivative of cotangent is cosecant squared, negative cosecant squared. We can adjust by multiplying with a negative, like this. So let's just find the antiderivative of this I part. The derivative of this part we need to differentiate is easy, it's just 1. So this I part, antiderivative of this I part basically is going to be, take the negative in, negative antiderivative of cotangent theta times cosecant squared theta d theta. This is just going to be cotangent squared theta over 2. You can do u substitution if you want, but that's this part. So our integral is now going to be, this negative is outside, negative theta as it is, theta times cotangent squared theta over 2, evaluated from pi over 4 to pi over 2, minus, and a minus of integration by parts will make a plus, integral from pi over 4 to pi over 2 of cotangent squared theta over 2, and the derivative of just this theta is 1, so 1 times this, or simply just this d theta. Now for pi over 2, cotangent of pi over 2 is 1 over tan of pi over 2. Tan of pi over 2 is infinity, so we basically have 1 over infinity for cotangent of pi over 2, which basically blows up to 0, and square of that is still 0. So for pi over 2 this just became 0. For pi over 4, the tan of pi over 4 is 1, and 1 over 1 is 1. So we have minus minus plus for theta pi over 4 times this half times a 1, which if even if you don't write, it doesn't matter, plus half of integral from pi over 4 to pi over 2. I'm going to use square identities now, because cotangent squared theta can be expressed as cosecant squared theta minus 1 d theta. This gives us pi over 8, and we have two integrals now. Half of integral from pi over 4 to pi over 2 of cosecant squared theta d theta minus 1 over 2 integral from pi over 4 to pi over 2 d theta. Now integrating this is easy. We have negative half cotangent theta evaluated from pi over 4 to pi over 2, and then we have minus half theta evaluated from pi over 4 to pi over 2. So at pi over 2 this will go to 0. At pi over 4 we have a 1. So this is nothing but pi over 8 minus minus plus half, and this is minus half pi over 2 minus pi over 4. So we have pi over 8 plus 1 half. This inside quantity is going to be pi over 4 with a negative half outside. So pi over 8. These things cancel out. So I is just half, or 0.5. So that's question 11. Let's move on to the next question on the fresh page. See you there. Moving on to question 12 now. Let's define I as integral from 0 to pi over 2 of sine of 2x times cosine of x dx. So notice we have a double angle and we have the single angle. So we can either convert the single angle to a double angle or the double angle to a single angle. But notice we have like a compound function here. So cos inside a cos for the single angle case. So converting this into a double angle is quite cumbersome and pointless. So it's worth converting this double angle of sine into a single angle, and even the formula is easy for that. So notice sine of 2x is 2 times sine of x times cosine of x. So I just becomes integral from 0 to pi over 2 of 2 times sine of x times cosine of x times cosine of x dx. So notice we have a cosine here, a cosine inside, and a derivative of cosine over here. So we can make a substitution based on these observations. So let u equal cosine x such that du is nothing but negative sine of x dx. So our integral is now negative cosine of 0 is 1, cosine of pi over 2 is 0. We have a 2, and then cosine x is u, cosine of cosine is cosine u, like this, and then sine x we compensated with a negative, so this everything else just becomes a du. And we can use this negative to actually correct the order of integration from 0 to 1 of u times cosine of u du. Now integration by parts as simple as always. So this is the function we need to differentiate, and this is the function we need to find the antiderivative. So antiderivative always in both cases, sine of u as it is, evaluated from 0 to 1 minus integral from 0 to 1 of sine of u du, because derivative of u is just 1. And when we calculate this, we have a 2, right? We don't forget the factor of 2 with everything. So this will just become 2 times 1 is 2 times sine of 1, and then for 0 and times sine of 0 is 0, so 0 minus, integrating this is easy, we have 2 times negative cosine u evaluated from 0 to 1. So this will become 2 times sine of 1 negative negative cancel, plus 2 times cosine of u evaluated from 0 to 1. So this is 2 times cosine of 1 plus 2 times cosine of 1 minus cosine 0 is 1, so we just have 2 times 1 or 2. That's I, and we can't simplify further because 1 radian, there is no standard value for 1 radian, it's not even a standard angle. If this were 0, we could have simplified everything, but it's 1 radian, so don't mind anything, just leave it as it is, that's it. Okay, so now we have I is equal to integral from 0 to 2 pi of sine of x minus x dx. So in cases where you have such compound trigonometric expression, so one trigonometric expression inside another and nothing else, that's when we have a um, good plan of trying to use symmetry. That's when symmetry is what's required, as long as you have definite integrals on such intervals. So when we do that for using symmetry, in place of x we just substitute 2 pi minus x and the rest is unchanged. So I is basically integral from 0 to 2 pi of sine of instead of x 2 pi minus x. So why 2 pi? It's because upper limit plus lower limit. So 2 pi plus 0 plus 0 minus x. So upper limit plus lower limit minus x minus 2 pi minus x instead of in a bracket like this dx. So this is basically integral from 0 to 2 pi of sine of 2 pi minus x is negative sine x. This will be negative 2 pi plus x dx. And we can take a collective negative outside, and sine of a negative angle is negative sine. So take a negative outside, integral from 0 to 2 pi of sine of, we took a negative out, so we have 2 pi plus sine of x minus x dx. And as long as it's angles we are talking about, this 2 pi acts like a 0 in an argument of a trigonometric function, because if you draw your angle representation, this over here we have 0 or 2 pi or 4 pi or any even pi, and here we have pi or 3 pi or any odd pi. So 2 pi is as good as this point 0. So it's almost like having 0 as long as it's inside an argument like this, because if this 2 pi were outside, then it would be approximately 6.28 if it were outside the argument. But as long as it's inside the sign, it's treated as an angle, and angle 2 pi radians is as good as having a 0. So by equivalence of these angles, we have integral from 0 to 2 pi of sine of x minus x, because this can be treated as a 0 dx. But notice what this thing is. That's just our I, right? Our original I that we started with. So I is basically equal to negative I. If you add both sides with I, 2I is equal to 0. I is 0. So all this trouble with symmetry for nothing. Now question number 14 is actually a really good question. Probably the hardest in the 1 to 20 questions of the qualifying round. So I is basically integral of 1 over x minus 1 plus sum from k equals 0 to 2018 times k plus 1 times x to the k over another sum from k equals 0 to 2019 of x to the k dx. Since it's an indefinite integral, we can split these two up. So if integral of dx over x minus 1 plus integral of sum from k equals 0 to 2018 of k plus 1 times x to the k divided by sum from k equals 0 to 2019 of x to the k dx. So this is easy, this is pretty elementary, we can do it in the end. It's actually this we need to simplify. So notice we have a k plus 1 and an x to the k. So this looks like a power was brought down and x to the k has a new power. It's almost like this resembles the derivative of something. Because if you differentiate a polynomial expression, say x to the n with respect to x, you get n times x to the n minus 1. So we essentially bring the power down. So it looks like the power has been brought down here somewhere. And the entire sum has been re-indexed because there is the lower sum starts from 0 to 2019 and then upper sum is from 0 to 2018. So it almost seems that the derivative of the denominator is somehow in one way present in the numerator. So it would make sense to let u, or have a substitution, let u equals sum from k equals 0 to 2019 of x to the k. And if you differentiate this, du is nothing but sum from k equals 0 to 2019 of k times x to the k minus 1. So if you want some perspective, if you write some terms, for 0 we have a 0, and then for k equals 1 we have 1 times x to the 0 plus 2 times x to the first power plus 3 times x squared, and that goes on till the last term, that is 2019 x to the 2018. It's a finite sum. So notice that for k equals 0 we are starting with a 0. So why not exclude that term? Why not start with 1? Because adding with a 0 doesn't even affect the value of the finite sum. So why not start with 0? Because k equals 0 is anyways going to be 0. Starting with 1, because anyways the first term is 0, is not going to change the value of this. But at this point we can still re-index it, because this is just exclude the 0, this series. So remember the top part started with 0. So if we start our index from 0, k equals 0, instead of going to 2019, we would have to go to 2018, right? And then we would have to add 1 and then add 1 here. So k plus 1 minus 1. And if you want to write the value, check whether these two are equivalent, you can write this out separately. So if you write this out separately, you have for k equals 0, you have 1 and x to the 0, this term. And then for 2, k equals 1, you have 2x to the first power, this term. So if you write some more terms, you know that they're matching actually. That this equality holds, because both these series are matching. So this means du can be written as sum from k equals 0 to 2018 of k plus 1, the ones cancelled out, so x to the k, don't forget the dx, I had forgotten the dx here. So, and this is exactly the numerator that we started with, this. So it's simple now. So our I will be integral of this is natural log of absolute value of x minus 1. So natural log of absolute value of x minus 1 plus integral of du over u. The denominator we let u, we call that u, and the Numerator is just du. We calculated that. So, this significantly simplifies our sum, which looked kind of intimidating at first, but we simplified it. Natural log of absolute value of u plus constant of integration c. Now back substitute, what was u? This thing. So you have natural log of x minus 1 plus natural log of sum from k equals 0 to 2019 of x to the k plus c. So now this, we have a series inside a natural log, and this series, if you want to write some terms, is basically x to the 0, which is 1, plus x to the 1 plus x to the 2 plus dot dot dot, that goes on till x to the 2019th power. So it's a geometric series with common ratio x and first term 1. So there's a formula for that. Sum of finite geometric series a times common ratio to the nth power minus 1 over common ratio minus 1. N is the number of terms. So the number of terms we have here is, these will make 2019, and then this first term is 2020. So we have 2020 terms. So using the sum formula for the geometric series, a is 1. We just have common ratio r is x to the n is 2020 minus 1 over 2020 minus 1, which is 2019, plus c. We can still do a slight simplification here. You have some natural log of 2020 minus 1 minus natural log of 2019 plus c, and this is a constant and this is a constant. So sum of two constants is another constant. So natural log of x minus 1 plus natural log of x to the 2020 minus 1 plus c dash, which is basically the sum of these two things, another constant. So that's basically our final answer. It looks intimidating at first, but once you get to do the derivative, substitution, reindexing and stuff, it actually simplifies down. Okay, so question number 15 is integral from 0 to pi over 2 of dx over tan to the square root of 2020 x plus 1. So it's basically tan x raised to the square root of 2020. It's a weird power, and trust me, this is really hard to do without elementary techniques. I think it's almost impossible. But in cases like these, we always try to convert the tan into a sine and cosine. So dx over sine to square root of 2020 of x divided by cosine to square root of 2020x plus 1, and this we can write as integral from 0 to pi over 2 of, taking that common LCM, cosine to square root of 2020 x divided by sine to square root 2020 x plus cosine of square root 2020 x dx. Now let's apply symmetry, and the way we're going to apply this is x we can change as upper bound plus lower bound minus x. So pi over 2 minus x basically, and all the rest is unchanged. So integral from 0 to pi over 2, we have cosine of root 2020 power pi over 2 minus x divided by sine to a 2020 power pi over 2 minus x plus cosine to the 2020 power pi over 2 minus x dx. And we can use the complementary angle properties of this. Cosine of pi over 2 minus x is just sine, doesn't matter to which power, of x, divided by, this will be cosine to the square root 20 of x. This will be sine to square root 20 of x dx. Okay, so this is I, and also this is I. So let's add both of these together. I plus I is 2I, and we have integral from 0 to pi over 2 of sine to the root 20 of x plus cosine to the root 20 x. Since both of them have a common denominator, I'm just grouping the terms together, divided by the common denominator of cosine to square root 20 x plus sine to square root 20 x dx. Notice the numerator and denominator are just the same, so they will factorize out to 1. So 2I is just integral from 0 to pi over 2 of dx, which is basically x evaluated from 0 to pi over 2, which is pi over 2 minus 0. So 2I is nothing but pi over 2. Therefore, I is dividing by 2, pi over 4. And that's the final answer. Okay, so moving on to question number 16. I is defined as integral of x times 1 minus x to the 20 power dx. So whenever you have a linear times another linear raised to a crazy power, what you do is you try to make the free linear one that is raised to, which isn't raised to any power, try to mimic whatever was inside here. So 1 minus x, we want to make this x look like 1 minus x. So to do that, I'm going to have to multiply by a negative, and not only that, I'll have to add and subtract by 1, because that will give us 1 minus x plus 1. So 1 minus x to the 20 dx. So now I have minus 1 minus x times 1 minus x to the 20, and then this other part, sorry, this is minus 1, add and subtract by 1, minus minus plus integral of 1 minus x to the 20 power dx. This is easy, right? This is 1 minus x to the 2021 power dx, and integrating this is easy. We have 1 minus x to the 2021 over 2021, but we have to also divide by a negative because we had a negative x inside. This can also be done easily. 1 minus x to the 2022 over 2022. Negatives were cancelling out. Minus 1 minus x to the 2021 over 2021 plus c. And hey, look at that. We got rid of the 2020s. We have 2021s and 2022s. The years we hope everything will be okay. You know, the years we want to just fast forward to. So anyways, that's how you solve such questions. So moving on to question number 17. I can be defined as indefinite integral of secant to the fourth of x times tangent of x over secant to the fourth of x plus 4 dx. So now we can split the denominator in terms of secant cube of x times secant of x times tangent of x over secant to the fourth of x plus 4 dx. And at this point, if you have a really good eye, you might know that the derivative of the denominator is present on the numerator. So this calls for a good well-intentioned substitution. U is equal to secant to the fourth of x plus 4 So du is just 4 times secant cube of x times the derivative of secant of x by the chain rule is secant of x times tangent of x dx. So notice that the numerator is just 1/4 of this expression. So on top we have 1/4 of du, and in the numerator denominator we have just a single u because of this substitution. And doing this is really easy. We have 1/4 times absolute value of natural log of absolute value of u plus c. So 1/4 times natural log of, all of this is always going to be positive, so no need for absolute value, secant to the fourth of x plus 4 plus constant of integration c. That's the answer for that. People can tend to get confused by trying to basically obtain a secant squared, because we see a tan and we are like, uh, let's make a u is equal to tan x substitution and we can hopefully simplify stuff, but that may or may not work. I haven't tried that, but it's a really long and cumbersome method. Instead, using the secant is extremely elegant, if you can see like over here. Okay, question number 18 now. I is defined as integral of x to the 2x times 2 times natural log of x plus 2 dx. And if you have any practice with differentiating variables of this form, variable to a variable, so if you have a variable raised to a variable, if you have practiced differentiating such things, then this term over here might seem familiar. It may seem like variable to the answer to this. So let's just, for our fancy, let's try to differentiate this. So let's call it another variable, y is equal to x to the 2x, and this is not a like a real substitution as now, like it's not like a u substitution that we have for integration, but more like a substitution that we need for differentiation. And then if this works out, then we'll calculate dy and dx and stuff. So anyways, we have natural log of y, we can take natural log on both sides, is equal to natural log of x to the 2x, which is basically 2x times natural log of x using log properties. Now differentiate both sides. So we have to do implicit differentiation over here. 1 over y times dy over dx is basically, now chain rule here, product rule rather, x times natural log. So when we differentiate x, natural log is as it is, if derivative of x is 1, plus x as it is, derivative of natural log is 1 over x. So this goes to 1. This will become 2 times natural log of x, and 2 times 1 is 2. That's 1 over y times dy over dx. So certainly the derivative of this has a form that we've bracketed over here. So dy over dx is y times 2 times natural log of x plus 2. But what was y? Just this thing, right? So derivative with respect to x of x to the 2x is basically x to the 2x times 2 times natural log of x plus 2. So let's make the substitution in place of all of this. Let's make this substitution. So I is basically integral of, instead of this, the original integrand, we can write this as a derivative with respect to x of x to the 2x power integrated with respect to x. Now using fundamental theorem of calculus, the antiderivative of a derivative, or the indefinite integral of a derivative, is just the function itself. So x to the 2x plus constant of integration c. And that's the way we solve this. Just using a clever observation that this could be the derivative of a function of the form variable raised to variable. So we had x to the 2x here. So now moving on to our penultimate question for the day, question 19. So I is defined as integral from 0 to 1 of square root of 1 minus x squared dx. So looking at the form of this is like a standard form. So it actually calls for a trigonometric substitution. Let x is equal to sine theta, because we can exploit the square identities of trigonometric functions with this. So I is just integral from 0 to pi over 2. You can check what theta is inverse, sine inverse of x. So you can check, you get 0 to pi over 2. Square root of 1 minus sine squared theta, dx is cosine theta d theta. 1 minus sine squared theta is cosine squared theta. Root of that is just cosine theta. So integral from 0 to pi over 2. We have cosine and a cosine. So cosine squared theta d theta. And cosine squared theta can be expressed in terms of double angle formulas as 1 plus cosine of 2 theta all over 2 d theta. So we can split this up into two integrals now. Half integral from 0 to pi over 2 of just regular d theta plus half of integral from 0 to pi over 2 of cosine of 2 theta d theta. This is easy. Integrating this is easy. We have half theta evaluated from 0 to pi over 2. Integrating this is also easy. We have 1 over 2 times 1 over 2 because we have a 2 in the argument. So chain rule, reverse chain rule rather, dividing by the coefficient. And then we have sine of 2 theta evaluated from 0 to pi over 2. So this will be pi over 4, and for 0 everything will go to 0. We have 1 over 4 sine of 2 times pi over 2 is pi minus sine of 0. Sine of 0 is 0. Sine of pi again is 0. Sine of actually any integral multiple of pi is 0. So all of this is going to 0. All we are left for our I is basically pi over 4. So this is actually the technical, the systematic approach of solving integrals of this form, square root of some quadratic. But if you want a more graphical or geometric approach to this, notice square root of y equals square root of 1 minus x squared is an equation of a semicircle in the positive y plane. So say if you have your coordinate axes like this, x and y here, so square root of 1 minus x squared is basically a semicircle like this, which has a radius of 1, because we have 1 minus x squared, not anything like, not something like 4 minus x squared, in which case the radius would be square root of 4 or 2. So radius is 1 like this, and we are integrating from 0 to 1, so it's basically area under this, whatever I'm shading here like this. We want to find the area of this. So notice this is just 1/4 of area of a circle. But what's the formula for the area of a circle? Pi r squared. What's the radius? I just said it's 1, right? So pi times 1 squared is pi. So 1/4 of area of circle of radius 1 is, which is pi. So pi and this 1/4 factor will give you pi over 4. So that's a quick way of doing it, and that's exactly what we got here, pi over 4. So you can do this by this approach or by this approach. I don't know which one was acceptable in the exam, but I just like to do everything technically. So question number 20, the last question, can be seen as an eliminator again, because this last question was basically to screen between the people who know some non-elementary stuff compared to people who are just sticking to their elementary integration techniques. So we had integral from 0 to infinity of x to the 5th times e to the negative x to the 4th dx. So what will we do now? It's just atrocious. The powers are crazy. So let's split them up into integral from 0 to infinity of x to the fourth times x times e to the negative x to the fourth dx. But still, how does that help? So integral from 0 to infinity, write x to the fourth as x squared x as it is, and e to the negative x squared dx. Notice that the derivative of x squared is in the numerator. We have an x, but derivative of x squared is 2x. So let's multiply and divide by 2. So now making the substitution, u is equal to x squared, du is 2x dx, and 2x dx is just here. So we have our du in present. Our integral now becomes half of integral from 0 to infinity. The upper and lower bounds remain the same. That's the great part about these 0 and infinity. Like for such simple substitutions, it doesn't matter. So we have u squared times e to the negative u squared du. Well, this is almost to the form of a Gaussian integral, but still it's not exactly. But we can still resort to gamma function. So let's do another substitution. Let w equal to u squared such that dw is equal to 2u du. So du, after making appropriate substitutions, is dw over 2 times square root of u. So I now becomes half of, remarkably upper and lower bounds are the same. Integral from 0 to infinity of u squared is w times e to the negative w, du is dw over 2 times square root of w. Take the 2 outside, we have 1 over 4 times integral from 0 to infinity of e to the negative w times w to the 1 minus half is 1 half dw. And notice this is gamma of whatever power w had plus 1. So gamma of whatever power w had plus 1. So gamma of 3 over 2 basically. But we can use this property of gamma. Say if you have gamma of 1 plus z, this will be nothing but z times gamma of z. So z in our case is half. So we have 1 over 4 times 1 over 2 times gamma of half using this. So we have I is equal to 1 over 8 times gamma of half. And if you know your gamma functions really well, so if you know your gamma functions really well, and that's why I call this an eliminator, because people who don't know the gamma function will struggle with this thing. They won't get a definitive answer. Gamma of half, if you know your gamma function really well, is basically the complete Gaussian integral from minus infinity to infinity of e to the negative x squared dx, which is square root of pi. So that's why we have 1 over 8 and gamma of half is square root of pi. So I is essentially square root of pi over 8. That's the final answer we end up with. That was all 1 to 20 questions of MIT Integration B qualifying round 2020. All the 20 questions. If you include part 1 and this video part 2. And that's it for today. See you next time. So please like, share and subscribe to my channel, guys. Recommend me to your friends. I really want to grow as a YouTube creator. I need more subscribers. You can follow me on Instagram, gamma_digamma. And in the meantime, have a great day. Stay home, stay safe. Don't forget to enjoy doing math, and peace out.